Thank you very much for inviting me, Peter, to come here today. My name's Sangwin. I'm from the Maths Department at University of Birmingham, and I'm a member of staff in the Maths Stats Know network. When I came here last time, I spoke about assessment, computer-aided assessment, so I've chosen something rather different this time, which is less in a research vein, and more in a vein of something that's really quite significantly changed the way I teach. And it's GeoGebra, so I've slightly cheekily titled this, I did this in my class and it worked, just to indicate this is less research and more about teaching development. Okay, so GeoGebra is some computer software designed by Markus Hertenwerter as his PhD project in Austria. And it's dynamic mathematics for schools. It's very much designed for schools, but I wanted to explain the extent to which it can be used in higher education maths. So that's what I thought we'd do. So this is the software. It's a Java applet. It's free to download and it will install itself if you go to the website, so it's very easy to install. You don't really need to install it, although you can for offline use like this. I'm just going to maximise this window, and you load it up. It's got the geometry area, it's got an algebra window, and it's got an input bar. We'll come back to those in a minute, but for now I'm going to just get rid of the algebra window, and because we're thinking about geometry, I'm not going to view the axes, so this is just a plane. And this owes its origins to dynamic geometry systems in which you can create an object like a circle, so you have the circle centered at a point and through another point. And then you can do things like putting a point on the circle. This point is now constrained to be on the circle, so on. So if you've seen these dynamic geometry things before, it's all quite familiar, I hope. This is very easy to use. If you notice on the right here of the icons, there's a little pull down arrow, and if you click on that pull down arrow, so if you go to the bottom right hand corner, you can pull down the menus. So we've got a new point, intersection between two objects. So if we add a line, choose the intersection between two objects, and we choose that line and that circle, then we get there. It's okay. So there's all that kind of stuff. So we've got points here, then we've got lines and line segments, arrays and things. These ones are a little more interesting perhaps. Perpendicular line, so we can now take the perpendicular line through that point, and then as we move, it's dynamic, so it does what you'd expect. Various circles, semicircles, arcs. This one is quite nice. There's a unique conic section through 5 points, and as you drag the points. And then if we go back to this menu and look at the tangent through that, we've got tangents to a conic. Okay, so that does all that kind of stuff for you. So, right, so this is clearly all to do with pure Euclidean geometry. If we go back to view the algebra window, as you move these points, you get the coordinates, and they all update. If we view options, font size, 18, I mean, you can make these things bigger, might be slightly easier for you to read. I'm going to just start again, just because it's a bit cluttered. So we've got a point and we've got its coordinates, and as it moves it updates them. If we put a line in, we actually get the equation of the line. So GeoGebra has I think, quite an unusual tight interaction between the purely geometric and the purely algebraic. And I think that's one of the most interesting things about it, and one of the things that sets it apart from the other dynamic geometry systems. So what I'm going to do is I'm going to go on to talk about what the software does and show you some of its other features. Then I'm going to talk much more about this interaction between algebra and geometry, and then I'm going to explain how my students have used this in a course.
In the graphs that you copied and pasted into other documents?
I'll explain exactly how you can get. Yep. That will be one of the things we'll talk about, is how GeoGebra actually interacts with other software. Okay. Right. So here is the line. You can move the line around, and you can see here that it gives you the equation of the line. Another thing which is this interaction between algebra and geometry is that this input field at the bottom. Maybe again I should. Was it options, font size? Make it a bit bigger. Okay.
Can you change the equation into the normal y equals mx C type, or does it come out in that format?
That's just the form it displays in. If you want to type in the equation y equals 3 times x plus 5,
yeah, okay.
then you can certainly type in this equation. So what you can do, again, file, new, we don't say that. So what I'm going to do is I'm going to start with the equation y equals x squared. So it plots that. That was a purely algebraic operation. I'm now going to interact with this thing geometrically to put a point on that curve and to drag the point. So that's now a geometric behaviour.
That's brilliant, isn't it?
And we could even go for the tangent to that object through that curve. And as we drag it, and you get the algebraic object, the line A, back again. So you've always got this interaction between algebra and geometry, which I think certainly for school is excellent, but it certainly has its uses for what sorts of things we're doing. I wanted to show you an example from my final year dynamics course. As you can see, I mean, this has changed the way I teach, because I'm not drawing diagrams on the board and pointing at them. I was teaching a final year chaos course, and you don't really need to know very much about it, because I'll just run through the kind of thing I would do in a class. Well, I'm interested in, so what do I need? I need a slider. So let me just set the scene a bit with a slider. We'll call it A, and it goes between 0 and 1, and we'll have very small intervals, and we'll make the slider fairly large. So I've now got an algebraic variable in my world, and it's a free object. I'm able to adjust that free object with the moving tool. Okay? And I'm also interested in the quadratic a times x times 1 minus x, which is an algebraic object, and it's the quadratic which has roots 0 and 1, and the maximum is a over 4, which is halfway between them. So as I drag a, you can see that what happens to that quadratic. Now if we type in the line y equals x, I was actually interested in it's an iterated function system where you put in a number and you get it out. And so I was actually looking at the logistic map and iterating that. And so the fixed points will be the intersection between the curve y equals x and the actual quadratic. And then as you can see that there's always 2 fixed points, one at the origin and one somewhere else. And the stability of the fixed point is given by the tangent to the curve through that point. And in particular, when the tangent is between minus 1 and 1, okay, so what I've done here is I've drawn the tangent. This is the tangent, this is the normal, and this is y. It's all getting a bit cluttered, isn't it? Right? So all you have to do is right click on this, go down to properties, let's just change the colour to blue, and then if we copy the visual style of that object, okay, right. So it's now much more obvious what's going on now. We've got the curve and its tangent, and then we're looking at when that tangent lies between 1 and 1. So if the tangent line lies between these, then we're stable. Okay? And so as A increases, the stability of that fixed point changes from stable to unstable as the tangent goes through 1. Okay? And what you do in your chaos course is we're interested then in looking at orbits of period 2, which are fixed points of f of x. So if we plot the graph of f of x, as we increase the value of a, at precisely that moment that the fixed point becomes unstable, we get two new fixed points of this map come into existence, the roots become real, and we've now got these d and f, and those are the new fixed points. And then we can do that again. We can look at the tangent of that point through that curve and the tangent of that point through that curve. They're interesting that they're parallel and that they always remain parallel, and at exactly the moment that they become unstable, f of f of f of f of x, I got that wrong. At exactly the moment they become unstable, this becomes stable. So, right, so I'm not actually pre-preparing anything here, am I? I'm just doing it as I'm talking, and it's so easy to use that there's really not a lot for me to do. That's obviously because I've done this a lot of times. As a new teacher, you can view the navigation bar for construction steps, and you can just step through it. And at each stage you can manipulate things, and then you can just carry on. Okay, so at each stage you can manipulate things and carry on. So you don't have to actually do what I've done to get started. You can pre-prepare something quite complicated and then interact with parts of it as your discussion progresses. Yeah. So let me just, by right-clicking on something, you can actually hide the object, which is quite useful for obscuring construction objects that don't really play a significant role. And we'll undo that. Everything can be undone, so there's an undo and a redo, as you might expect. You can show the label, you can turn the trace on. I'll show you some examples of that in a minute. Rename, redefine, delete. Properties is probably the most interesting. Basic properties, you can call name, definitions, colour, let's make it a red colour. Let's have a very thick line, which is dashed, and let's have 25% full. Okay, and then there's the equation of it and various other things. So you know you can make these things look very attractive very easily. I'm beginning to lose track of where I was going. Okay. So I've talked about pure geometry, dragging and manipulating. It's not obvious why we've got these buttons. Why are some buttons there and some buttons not there? They're not all Euclidean axiom buttons. One of the things in Cabri is very much tied to Euclid's axioms, whereas this isn't tied to Euclid's axioms. We'll talk about which buttons are there and which buttons are not. We talked about algebra entry. You can type in the algebraic expression of an object, not just create it with the buttons. The traditional calculus with this example with the tangent to the quadratic. And if you look on the website, I'm just going to flick to the PC. If you actually go to this is on the internet, whereas my laptop isn't. This is the website. Go to the wiki. Go to the English wiki. If we go to Maths High School, say algebra and pre-calculus, or
so
maths.
This is a wiki attached to the GeoGebra
website. Yeah.
So it's people putting stuff in about their experiences, and that's very good.
These are worksheets. If you go to the Taylor polynomial worksheet, Mike May is quite reliable. I checked this one out before the talk. And one of the things with GeoGebra is you can create web pages very easily. I'll show you how to do that in a moment when we talk about output formats. But he's created, this looks like a terribly complicated applet. So I'm going to just turn down, you're approximating the function. This is the function you're approximating. Let's just do sin x. Okay? So let's find the Taylor polynomial of sin x. There's sin x in the GeoGebra window. We'll approximate the Taylor series of sin x at x equals 1. And we've got, so n equals 0, it's just the Taylor polynomial at that point is just a constant. N equals 1, it's a straight line, it's a quadratic, it's a cubic, and you can see the green Taylor polynomial approximating sin x better and better. And then you can look at the error. E1 is the error between the Taylor polynomial and its real function at different points, and all these nice pre-prepared things. And Mike has done this, and so you can set all these values and change the function and all this kind of stuff. So all this is available freely online. That's all there. I haven't posted many online, and I don't use the ones online because I would rather, certainly at university, show my students how to make the worksheets live in class than have some whizzy pre-prepared thing. I think it's more honest for them. So I tend to pre-prepare as little as possible now. I am being videoed, but from a teaching efficiency point of view, you can spend an awful lot of time pre-preparing stuff. So it's nice to show the students, but also there's a sensible pragmatic issue here about how much time you want to spend on all this stuff. So there's accessibility. I mean, this is a difficult question because this geometry is fundamentally in the visual realm. So there's a limit to the accessibility features here, unfortunately. Nice things, you can resize all the fonts and stuff and change the colours, and they're nice non-serifed fonts. So there are reasonably sensible things you can do, but I'm not sure what's really possible there in a deeper way. Okay, pre-preparing worksheets and stepping through. I think I've sort of covered that. Including graphics. You can include pictures in these things. This is one that I've written. This is to illustrate a mechanism from an old steam engine. This is James Watt's linkage. To constrain a piston in a steam engine attached to the rod, you want the piston to move up and down vertically, that's the idea. And James Watt invented this mechanism. Here is the beam of the engine, and attached to the other end of the beam is the pump that goes down the mine shaft. And he wants this is moving in a circular arc, because it's a beam and it's pivoted here. But he's got a piston and it's going up and down in a straight line. He needs the piston to go in a straight line. So at the top of a cafetiere, you don't want the piston to be doing this, it's just going to wear and tear. So he needed this to move in a circular arc, but this to move in a straight line. And the mechanism he invented is this linkage. 1, 2, 3 bar linkage. And I've stuck a picture of it in the background. And I then made a GeoGebra worksheet over the top of that picture. And you can move the blue line, and that illustrates that that's a pretty good approximation to a straight line over the kind of range a piston might move in. But if you go down too far down here, say, it's on a curve. This isn't a straight line, it's only an approximate straight line. Yeah. Slightly more mathematical example. This one is off the internet.
So that image is part of the GeoGebra.
I've just
so you can copy and paste image.
Insert image, and then you just load it, and it sticks in the background. You can resize it, and then you can do your. So if you're modelling, what curve is the arc of this bridge? That's one of you mentioned Adrian Oldknow.
Yeah, I've seen him do that a lot.
So you can, yeah.
It's in the arc bridge or whatever.
Yeah, you can do that sort of thing here. This is a nice one that I loaded off the internet again for my final year chaos course. It's iterates of z squared plus c in the complex plane. And as you move this points inside the Mandelbrot set are either fixed or periodic, and points outside diverge. So by putting an image in the background, you actually can see what's going on really nicely. So that was images in the background. And the last thing I want to talk about is tools. So let's get rid of that. Let's get rid of James Watt's linkage. And let's go File, New. Okay, so let's imagine I don't have a button. There is a button that will find the centre of that circle. Okay? Right? So let's imagine I don't have that button. How am I going to find the centre of that circle? Well, what I'm going to do is put 3 points on the circle, and I'm going to find the perpendicular the line bisector of the segment DE and EF. Right? And where they intersect will be the centre of the circle. Right? So I've constructed, given the circle, I've constructed how to find the centre. All right, that's fair enough. Now I'm going to create a new tool, and the output object is going to be the point G. So that's the centre of the circle. And the input objects, well, we don't want the points that define the circle, because there are lots of ways of defining the circle. What we actually just want is the circle. Okay, so I've now created a tool. Yep. And if I draw another circle and use my tool, the input is a circle and the output is the centre of the circle. So you can encapsulate a sequence of construction steps that take geometric and or algebraic objects and produce another GeoGebra object, and these become buttons. Which leads you to the question of why these buttons were chosen in the first place. There's one button missing here, I think. One button missing that I realised was missing, and it's this button. So I've created a new button, and the button takes two circles. And you choose two circles, and it finds the tangent lines to both those circles. It was a nice little Sunday afternoon exercise to play around to work out how you do that, and having done it, you can then encapsulate that in a button. Because you can do this, but of course you can make a nice little icon if you so desire, just to make it look nice. Because there were all these other things. You can do tangents between a point in a circle, but you couldn't do tangent between a circle and a circle. Why are you interested in this? Well, this is currently one of my favourite pure geometry theorems. Take any three circles, find the external tangents to two of them. In fact, find the external tangents to them in pairs. Those will intersect if the circles are of different radiuses, and those are all on a straight line. So your only hypothesis is three circles, and so it's kind of nice little geometry theorems that you can do, which uses the button that I've just created. Slightly more serious or more useful, perhaps. Some of my students had difficulty visualising the geometric interpretation of complex arithmetic. Now, GeoGebra is not designed for complex arithmetic, it's designed for Euclidean geometry, but once you've got points in the plane and you've got some algebra, there's no reason why you can't do complex arithmetic. So, the first time I did this live in a lecture, and we worked out what it means to multiply two complex numbers together, and you can just type in the equation of the point that has the right coordinates based on the coordinates of A and B. And then you can encapsulate that into a button. So if we have the multiplication of A times B, that's the button C. So if we now move the point B multiplied by A, well, C is always the product of the modulus, and you can see it's always the angle ahead. So it's on the line through the origin. Okay. So I've actually got a whole range of complex division, conjugate, inverse, square root, and all that kind of stuff. But we just stick with the complex multiplication. Let's put a point on that circle, and let's do, whenever you define a tool, its name becomes a command as well. So if we do complex multiplication of f with itself, we're squaring a point. We're squaring the point f. So if we move this to be the unit circle, okay, and now we square a point on the unit circle. So obviously the modulus stays 1 and the argument is double the argument of f. So as we move f around the circle, g goes around twice. Just what you'd expect. Now if we haven't got the unit circle, what's the locus of g? Well, if we type locus of g as f moves, colour that, just so you can see the locus is red. As f moves around the circle, so g moves around twice around this cardioid. And as you move the circle, and you always get one of these kinds of cardioids, and whether it's got a real loop in it depends on whether the origin is enclosed. But I think this is quite a nice little visual thing, and again, we're using high school software. It does quite a nice job. So I think these tools have got some quite interesting possibilities as well. Okay. Output formats. The actual GGB format is very small. If you look at the files in my directory, these ones, The only one that's of any size at all, 48K, has the picture in it, so it's not a surprise it's a bit bigger. But most of these are 3 or 4K for these, the tangents to 3 circles, including the tool itself, is only 6K, it's nothing. So they're very efficient. They're actually zipped XML, so if you rename it to a .zip file, you can actually see what's inside it. You can export these, file, export as a picture. So encapsulated PostScript means it's a publication quality diagram. It's extremely helpful for getting accurate mathematical diagrams that are psychologically helpful, because you can create the correct diagram and then drag it so it looks nice, and then still get, which matters actually. It matters that your triangle doesn't end up being a right angled triangle when you don't want it to be a right angle. I mean, it really does, I think. So for my notes now, I always do my diagrams in this and export them. You can export them as ping images, scalar vectorable graphics and so on, or you can export them as PS Tricks code and just cut and paste it into LaTeX. It becomes part of the LaTeX document. So you can cross-reference between your figure and your LaTeX document. It's just really lovely. And then the other thing you can do is file, export as a web page. So if I just call it a great page, above, below, text after, export, and let's put it in, I want to put it in my temporary directory, and we'll call it demo. Okay. So what I'm doing is I'm exporting this whole GeoGebra worksheet as a web page, and it's loading it up in the browser. There we are. Well, I have to say run it. Yeah. And you immediately get yourself a web page that you can just post on the internet. It includes the Java applet, and the students can now interact with the Java applet just as they did, and you've got your web page for almost no cost. I mean, just as quick as that. I'm not sure which settings I used. Sometimes I think you can opt to double click on them and actually get the GeoGebra applet up. There are all sorts of options. There are lots of options about exactly how you do it. But it's as easy as that to make a web page. And I'm not going to demonstrate it, but there is a JavaScript interface. So you can write some JavaScript to load up a GeoGebra page to interact with other websites and web applets.
So to get into Word, you just convert the HTML to a Word document, or what?
I don't know how you get it into Word. It depends if you wanted it to be interactive or not. If you wanted the picture, you might be better off exporting a picture format and including that.
Yeah.
I mean, I sort of started off emailing pictures to students, but that was silly. You just email them the GGB file and then they can use it.
Yeah.
So
Yeah.
why you don't want the GGB format is the question to address more than anything else. Because the whole point of it is that somebody else can then interact.
If you could make a Word document dynamic.
We can maybe look into that later and give it a go.
Whatever.
If you can include a Java applet in a Word document, then you can include GeoGebra. That's the answer to the question. I think from a mathematical point of view, what's interesting about this is it mixes pure geometry and algebra, and that brings us to notions of a function. Currently, a function, according to Weierstrass, as I believe this definition goes to Weierstrass, is that we have a domain and a range, and that for each element of the domain, there's a unique element of the range. Okay. But there are other notions of function. This is from Hardy's Pure Mathematics. I was quite shocked when I went back and looked at this. And he says, we must point out that the simple examples of functions mentioned above possess 3 characteristics which are by no means involved in the general idea of a function. Y is determined for every value of x. To each value of x for which y is given corresponds one and only one value of y. The relation between x and y is expressed by means of an analytic formula. All that is essential is that there should be some relation between x and y such that to some value of x at any rate corresponding values of y. So he goes on to talk about algebraic expressions, infinite series, and then he talks about the relationship between x and y follow from some geometrical construction. So to Hardy, and explicitly says that to Hardy, a circle is a good enough function. Go back even further, look at Euler's Introduction to Analysis of the Infinite. He says, in volume 1, a function of a variable quantity is an analytic expression composed in any way whatsoever of the variable quantities and numbers or constant quantities. Hence, every analytic expression in which all component quantities except the variable z are constant will be a function of that z. Okay? If y is any kind of function of z, then likewise z will be any function of y. Now, he really means implicit functions here. In volume 1, Euler's notion of function is an implicit function, which is quite different. So to Euler, this is both function y a function of x and x a function of y, which is quite different from what we do. And a consequence of that is a function might be multiple valued. So we make a distinction between single valued and multiple valued functions. That's not allowed anymore, but to him, square root had two values. And they were perfectly happy to have two values as the result of a function, multifunction. So if this is his example, root of 2z plus z squared. Whatever value is assigned to z, the expression root 2z plus z squared has twofold significance, either positive or negative. And again, to Euler, at this point, a circle is a perfectly good function of x. X is a function of y, and y is a function of x. And it's not really nitpicking, it's an important restriction on what can be a function. Now that's interesting to contrast this with his second volume of this Introduction to the Infinite, where he says, thus any function of x is translated into geometry and determines a line, either straight or curved, whose nature is dependent on the nature of the function. And then a little bit later on, he goes on to say a curve can define a function. So in the first volume, his notion of function is an algebraic relationship between the variables. And in the second volume, it's to do with curves in space, the linking, the geometric notion of function. And all this, both of these volumes deal with implicit functions, not our explicit functions. And I like the way that that GeoGebra goes back to those kinds of notions of mixing the algebra and the geometry together. And I think we've lost sight of that a little bit in the way that we set out our curriculums at the moment. Okay, so what did I use GeoGebra for? As you can see, I've played around with it for my own satisfaction, to solve problems and to understand things better. I use it in lectures, but I also wanted to get my students to use it. And I was lucky enough this term between Christmas and Easter to teach a course. Code is MSN1Y. It's called Developing Mathematical Reasoning. And MSN1Y has been taught in Birmingham for a few years by a colleague, and it's a Moore method course. Moore was a Texan mathematician, and he believed in learning by doing rather than telling. And his method essentially consists of walking into the lecture theatre, writing up the theorem on the board and waiting for the students to solve it. And he would say, yes, that's correct, or no, that isn't. And so he does, as I said, you tell them rather little, that's what I've said there, and he really was pretty harsh about this. He taught topology using this technique, as did the colleague who'd run it before, to first-year undergraduate mathematicians. And I'm not so familiar with topology that I'd want to teach that, but also I'd rather felt that I wouldn't want topology in the first year in this sort of way. So I chose Euclidean geometry. It won't do them any harm, they won't see it anywhere else, and it wasn't a prerequisite for anything, so I had a bit of freedom, and this was approved to do this. So I chose Euclidean geometry, or theorems in Euclidean geometry. Here's an example. This is the first thing we did. A ladder standing on a smooth floor against a wall, slides down. So you've got a ladder, a wall. Along what curve does a cat sitting in the middle of the ladder move? Okay, that's the problem. Yeah. So this was my GeoGebra worksheet to explain to the students the kind of thing I was expecting them to do. So state the problem. We have to zoom out a bit because on my PC the screen is squarer. So I'll just zoom out a bit. Okay. There we are. So there's the point on the floor. Now, the point B is a little bit difficult to define. Come back to the fact that the text is all off the screen and the things are the wrong size, or we'll come back to that in a minute. We can define the point B, which is the other end of the ladder, as either the intersection of a curve of fixed radius with the y-axis, or we could just define it as the actual point 0 square root of 4 minus x of a is the x-coordinate of the point A. It's the only slightly counterintuitive thing I found with GeoGebra. To get the individual coordinate of a point, it's the function x of the point. That's the only thing that I had to email the list to ask for. Everything else is pretty easy. Okay, so let's do that. There's our circle, there's our point B, that's the midpoint, there's our ladder, and there's the cat on the ladder. Yep? So as we move the cat, so I've turned the trace on, which gives the game away a bit. So it looks very much like it's an arc of a circle. Yep. Then if we carry on with the steps, if we actually add another ladder through the point M, you can probably argue very easily now by similar triangles that it really is the arc of a circle, because the distance OM remains constant. You can, so anyway, nice little geometric theorem, or you can do it by Pythagoras, and again, and I've put some text in here to explain what's going on. Yep. So that was one of mine. Here's a problem that I posed my students. Two flat watches lie on a table, both of them run accurately. Along what path does the midpoint of the segment connecting the endpoints of their minute hands move? Right? Okay. I mean, the point of this course was that the students had to do the proofs themselves. You see, this was whether they actually learnt any deep geometry from this wasn't my goal. The aim was to have the students come to the board, present their proofs to the class, for the class to criticise them. That was the idea of this. So I didn't mind if they didn't cover a lot of curriculum here. Okay, so what did, this is one of my students did this is 28 star. And they posted these on the website for the course, so when they came into the lecture they just had to click on it on the website, and like I did with the wiki here. And so this is one of the students' work. There's a watch, there's another watch, there's the minute hand, there's the time, there's the 12, and so you can move the time. Yep. And then we've got the segment connecting the minute hands and the midpoint. Now the problem is that we don't know where the watches are, and we don't know, they're certainly not necessarily the same size, but what can we say about the locus of M as it moves? Well, it looks like a circle, doesn't it? Okay. So, and then I won't go through all this, but the student has written a proof and found the construction, and lo and behold, it does lie on a circle. Yep. So the students are actually using this to demonstrate their work in class, which is.
So you're looking for the proof, an algebraic proof?
Well, I mean, I really didn't.
This was a proof. Is not a proof, is it?
A picture isn't a proof.
That's right.
But there's a big difference between a purely geometric proof and an algebraic derivation, and that was one of the big points of discussion in the class of what constitutes a proof. And this is the best example of that, because I was just coming on to prompted exactly what I was going to do next. This problem caused huge controversy. Now this is one of the students' complete solution. This is what she submitted. Tools. View, I'm going to turn the navigation bar, I don't want to look at the construction steps, view navigation bar, okay. So you're given a circle, and are given a point on the circle, and you're given another point. And what you have to do is you have to construct an equilateral triangle on that line segment AN. Yep, and there are of course two equilateral triangles. And the question was, as the point N moves around the circle, what's the locus of the other vertex of the equilateral triangle? And some of the students got into terrible trouble with this, because they turned everything into coordinates, and they were trying to, find the coordinates of one term and that. And one student said, oh, well, all you have to do is, point M1 is just a rotation of N about A by 60 degrees. In fact, that's how this student, if you look at how this student has defined that point, rotate N by an angle 300 from A, because it's the anti-clockwise, right? Well, if N moves in a circle, and this point is that point rotated, it's going to move in a circle, isn't it? That's the locus. It's just this circle rotated by 60 degrees around that point. And we had terrible, and the students thought this was cheating. Is that really a proof? Is it that easy? So this business between a purely geometric proof, a proof which was using coordinates and which had more of an algebraic feel, and when you were allowed to mix these elements was really something we spent a lot of time in the class discussing. And the ability to mix those things here was really very helpful. Both to give them the answer, sometimes it was easy to get a geometric proof, sometimes the picture gave them the answer, and having seen the answer, the algebraic proof was neater. And we had all this discussion about what's allowed, am I allowed to use this proof, and all those kinds of things going on in the classroom. It was very interesting.
Yeah, what is proof?
What is proof, yeah. So there are a couple of other ones. So my take on Moore's method, doing not telling is a sound principle. I think Moore's principle is basically sound. And you have to allow the students to struggle, which is quite difficult for a lecturer to do. But unlike Moore, I really think the teacher should give detailed feedback on what they've written. Moore, pretty much as I understand his technique, just said yes or no, and the student had to spot their own mistakes or whatever. Whereas I really felt that when the student had done something, it's my responsibility as a teacher to get as much positive out of what they've done, without actually telling them how to do it. So if they've got a good idea, but the whole thing's, I mean, some of the students were hopeless. They hadn't identified the givens, they hadn't identified the goal, they'd gone off on some huge algebraic, but they might have had some nice ideas. So it was just trying to keep things moving. But not telling them the answer did require quite a lot of self-control. And it was very frustrating for the students, and it took a lot of time. We did 31 of these slightly trivial problems in 10 weeks. We didn't cover a lot of ground, but I absolutely think it was worth it. I really, really think the students got a lot out of it. They really liked GeoGebra, some more than others. The student I just showed you would do a perfect GeoGebra diagram like that, and then she would come and write her proof on the board. Because it's quite difficult to get the text into GeoGebra, and it's actually just not worth the time, I think. As you can see, it doesn't come on the screen in the right way, and it's just not quite right yet. So not all of them some of them liked it more than others. Some of them spent a bit more time on it than perhaps they should have done because they liked it so much, but that's okay. All of them thought it helped during lectures, but the facilities for proof were poor, and so I think that needs to be addressed by the developers. I'm talking to them about that. Because maths is about proof. I mean, that's my title here. Yes, a pretty picture's not enough. That's not the proof, is it? It's helpful, it's an important step in understanding the proof, but it's not enough. You've got to justify it. So I think my conclusion, and I should stop now because it's nearly 4 o'clock. I think GeoGebra is easy to learn. I really do. I think it's very useful for exploring maths in private because I certainly use it that way. I've pretty much given up doodling on paper for anything elementary now. I do my diagrams in GeoGebra. I mean, if I fess up to what do I use most, I use WinEdit, email, I look at pictures, I explore the internet, and I use GeoGebra. Those are my most used applications, right? So that tells you what I'm up to. So exploring maths in private, giving talks in lectures, it's changed the way I teach, especially with these interactive whiteboards in school. You can put your finger on it and you can pull that circle across. I missed a trick because I didn't bring my wireless mouse, or I'd have had you doing it in the class. And the students say, well, what happens if you do this? And you just give them the wireless mouse. Well, you do it. Have a look what happens. Okay? And I think it's very useful for students, for use by students in presentations, because they can pre-prepare their worksheet and step through it. Their drawing of circles on the board is terrible. I mean, it's just awful. So they can give a really professional presentation without having to develop all those motor board skills, which is really difficult for people to do. It's not perfect for proofs yet, and I think that's a good place to stop.
How did you assess them?
The assessment was in 2 parts. I took the best 2 presentations they gave. I took careful notes during lectures, and I took the best 2 presentations that they gave and marked the presentations against a set of criteria, such as they correctly identified the givens, they correctly identified the goals, the proof was logically sound, it was professionally presented, those kinds of criteria. They had to submit all the answers to all the problems. So this is a bit difficult because, on the one hand, we don't want them to copy each other, but on the other hand, I think it's rather unfair if they have to solve all the problems themselves, quietly on their own, because we never do that in a traditional lecture course. The lecturer tells them something, changes something, and they go away and show them that they can adapt what they've been seeing to what they've got to do next. So I didn't really think it was fair to have them doing all the problems in private and handing them in before the lecture. I was quite happy if they saw some somewhat incoherent discussion by another student, and from that got the idea that allowed them to write up their proof perfectly. And so I was quite happy for them to get the ideas in the lectures. I don't think that's learning, isn't it? I'm quite happy with that. So they had to submit all their work. They were allowed to use paper, GeoGebra, or a combination of both. They could upload files to my website. I mean, I've got a virtual learning environment where they can upload this stuff.
It seems to me that this helps them to think mathematically.
I think so, yeah.
So
I really think so.
It might be an interesting exercise next time, is to find out some base level of mathematical thinking that they, I don't know,
yep.
I'm just thinking aloud now, just
yep,
base level, and then say, okay, well that's what, you know, on average you all know this, and by the end, see where they are in the mathematical thinking skills. The connecting of the algebra with the geometry, I think that's terrific.
Yep. And also issues of precision and language. The students describe lines when they mean segments, and they talk about circles when they mean arcs. And with GeoGebra, you can be a bit more picky with that, and actually get them to start thinking more rigorously. I know these are apparently trivial details, but that's where the rot sets in, isn't it? And this is an opportunity to actually start describing some of those things more accurately. When they say, oh, let's take the segment, they're using the segment tool, so they know it's a segment, not a line. And all these little things actually contributed to what I thought was quite a successful class, really, even if I say so myself. I mean, it's nice when that happens. Well, I was very lucky. I only had 15. You can't teach in this style without 200, because everybody's got to have a chance to come to the board, and everyone's got to be patient, and you have to have a class dynamic. You have to trust each other a bit. So it won't work in large lectures, but then there are other ways you can use it. You can use it for presenting. One student could present something they've done to the whole lecture class. It all depends on the setup. But the Moore method, I think, will only work with groups of less than 50.
Three-dimensional version is an interesting one.
Sorry?
A three-dimensional.
Yeah, there's Cadbury 3D.
Yeah, but I mean this connecting the equations. And,
if you go to the feature requests on the website, there are a number of people who ask for 3D versions of it. I think that's
I think that's great.
Yeah. It's in the last 5 years, it's the thing that's changed the way I teach most, I would say. Which is,
I like the complex variable thing as well, because it's quite difficult to understand it when you see it first.
yeah. Yeah.
Thank you.
Thank you very much.
Yeah, excellent.